Hello again, now to the third part of the second lecture. We continue with a more advanced sparse row storage scheme, but it's not as general as the compressed sparse row scheme. Let's have a look. It's this scheme is used when we have small sub-blocks, and these sub-blocks arise in a very structured way, where these typical for matrices which arise in the finite element method, like let's say elasticity or fluid dynamics, where with one node we have a few unknowns related, and the structure will be copied to these unknowns. In essence, this format is the modification of the CSR format. So let's consider the following matrix. We subdivide this sparse matrix into m times n blocks. In our situation, in 2 times 3 blocks. Most times the subblocks are 2 by 2, 3 by 3, 4 by 4. But let's stay general. So we subdivide the matrix into subblocks. We see that not all subblocks there are a lot of subblocks where all the 6 entries are 0, and a few subblocks where there are non-zero entries. We store these subblocks in the CSR format, so depicted here by green and red and the yellow row and the remaining gray entries. So for this matrix of subblocks, we are using the CSR scheme, and each subblock, because we assume that all of these subblocks are more or less full, or most entries are full, we store it as dense matrix, dense matrix. We don't care about these additional zeros. The advantage is with small, would be some overhead, and that's quite efficient in specific matrices. Okay. What about the space complexity? To express the space complexity, we define 2 additional variables. Capital N is the upper Gauss bracket of n divided by s. So how many number and rows of submatrices will be needed for our matrix, and z will be the number of non-zero blocks. So it's the small z for our CSR matrix before, it's now the capital Z. And the space complexity now is the number of blocks, so that we have for each block we need s squared. If our matrix is an n by n matrix, we need this s squared times d times the number of blocks, and then we need the index for the column index for our blocks, and the other row index. The row indices are given by this row pointer b of corresponding to capital Z. In the situation that our blocks are not, we will not store them as dense matrices, we will store them as sparse matrices. You could think about that we have some CSR or some CSR block CSR matrix. But we will recognize that these blocks are, if they are small, then also the indices will be small, and it's more convenient to store these matrices as in the coordinate format for these subblocks. And additional, to be more efficient, is to have some ordering. So, for example, we store our entries of each subblock row-wise, collecting them together, that we have these vector of matrix entries, it's full, and for all entry we have the row and the column indices. Let's say from this case our indices are only from 0 up to 8, so there are only 3-bit would be enough to store this index, and also 3-bit for these entries, so that will be 6-bit. It's 1 byte would be enough to store the indices for each of these entries. Here we have only 8 entries, so 9 byte would be enough. So the overhead for storing the indices is quite small due to the fact that the range of for the indices it's small itself. The subblocks, again, we store as CSR matrices, where the data itself is a pointer to our subblocks. Good. What we have as the row storage scheme here, I'm sorry, other way around. It's quite efficient, this system, if we have some nice pattern, but this strongly depends on the matrix we have in mind. So let's summarize our lecture. So especially the analysis we have done about the space complexity. Just remind that the small z is the number of non-zero elements, that the E should be the number of non-zero elements per row, the maximal number, and is the number of rows and columns of the block matrices in the block CSR or sparse block CSR methods, and D is the number of bytes required for storing a single matrix element. So and just the G was the number of non-zero diagonals, especially for the compressed diagonal storage scheme. So summarize everything. So we get for the dense matrix, if we have a square matrix n by n to n squared by d, and this is a summarize of everything. But we see also for the coordinate we have, besides the storage for the elements, some overhead of 2bn times z for storing the indices. We are an implicit given, not directly. And if we compare everything for an example, that's given here. So the example I've used for the small MATLAB session called Keller matrix, which arises from the discretization of the Laplacian on a unit square, equal spaced, using the 5-point difference star. And do for this academic example show how the sparse matrix storage behaves. We see that for the situation that we have the lexicographical ordering, a specific case, asymptotically the storage behaves optimal. So the add-on for just the indexing vector, these are five diagonals. If n increases, 5 over n tends to 0, so that would be optimal. On the other hand, the very simple storage scheme, the coordinate scheme, here if we have 10 to the 8 degrees of freedom, we see that we're starting by 8, we double already the amount of space. And if you have 10 to the 8 and you double already, okay, it's, instead of 1 terabyte, you have 2 terabytes. It's small, it's only a small factor, but at the limit, it could be quite necessary to save also the storage. It's a story. Okay, and all the other methods are between. You already see that the CSR method, if you're in the mid-range up to the limit, is concerning the matrix storage. It's easy to handle, but it's quite not optimal for the matrix storage. But at the end, it's a few things to consider. It's the matrix storage, of course, but also the efficiency and the runtime. And here we see the runtime at the end. We have to take into account the which computer you're using, which problem you're solving, but to have all these things in mind. So To summarize, okay, we have to take into account, we would like to take into account the large amount of zeros it contains. Most common ways, non-zero elements, only the non-zero elements are explicitly stored, and the zeros are implied. Of course, this decreases the storage space, the add-on, and the bandwidth requirement, but it allows avoiding the trivial operations on zero elements. So this, sorry, was wrong. So decreases the storage space if we only store the non-zero elements. It decreases. But of course, we have some add-on due to the storage format. We have a higher complexity. It's more difficult to handle. Has a negative impact on performance. As you already got the impression that there's no straightforward way of constructing, that there is no straightforward way for constructing an efficient sparse matrix storage scheme. That we have general formats like the CRS, respectively CSR format, that we have specialized formats like the block CSR, that we have storage schemes optimized for specific architectures, like the jack diagonal format for vector computers, and that all these current formats suffer from several drawbacks. While you're doing the exercise, you will see that the short vectors, that means that you don't have a lot of non-zero entries per row, and then that may vary the length of entries per row. It's a drawback, or that we have no highly efficient storage scheme. The index access, if you try to delete or one entry, add some entry, it's time consuming. And that you also have some overhead for the position you like to store. So at the end, we will say, okay, storage schemes, it's complicated. It depends on the problem. It depends on the problem size, on the architecture, and you get your own impressions how it affects the runtime and the storage. So at the end, I would like to ask you to work on two more or less interesting and simple exercises. So write a code or a pseudocode for multiplying a sparse matrix. Let's say in one of these formats, just take a simple one, the compressed diagonal storage format, by a dense vector, to get a feeling how complicated it is, what are the mouse traps. And another exercise would be how would you design a matrix storage scheme for a symmetric, positive definite matrix, like the finite elements matrix we see later, with direct access to the diagonal. Due to the fact that we have a symmetric matrix, we only have to store the lower or the upper part of the matrix, plus the diagonal. And think about how you would design a matrix scheme and how you would design the matrix vector operation. Okay, I hope you enjoyed this kind of online lecture, and yes, let me know if you have any recommendations or if you like it. So, bye. Oh, what I forgot. So the next lecture then will be on Laplacian on the unit square.